In this video, I will review the homework from the last lecture in the review of pre-calculus and calculus before we start actually learning new concepts in Calculus 2. The lecture is called Integration by Substitution, and the idea is just like anything pretty much in Calculus 1 is very simple. The integration by substitution is just undoing the chain rule, but we're not gonna undo it as a formula. We're gonna undo it. We're gonna learn a whole process called substitution that allows us to undo the chain rule. And the goal here is to learn how to, well, first learn the process and then learn how to identify the situations where this process can be applied. So let's jump right into it, and we have an integral. And here's how substitution works. When you're doing substitution, you kind of have to announce it. You have to say, I'm doing substitution. And when you're doing substitution, you have to introduce a new function. I would encourage you not to use letters U and V because those will be reserved for integration by parts. So I always use letter T for substitution, and we don't call it U substitution, we just call it A substitution. It doesn't matter which letter you use. And you will learn to recognize what to substitute, but the rule of thumb is kind of take the ugly part of your integral and try to get rid of it. That's kind of the main idea. And in this case, we have introduced T as the radicand, so what's inside of the radical, and dt will be, and now we have to differentiate this function, so it's going to be a 6x dx, and here we can already see how to apply the substitution, right? So we're going to divide both sides by 3 over here, so now we know that 2x dx is actually equal to 1/3 of dt. And once we figured out all the ingredients of the substitution, we kind of close that bracket and we start substituting. So we have an integral. Instead of 2x dx, we're going to write 1/3 dt. And instead of square root of 3x plus 7, we're going to write square root of t. And you can see how this integral immediately became a very simple integral. So we're going to write it as t to the power 1/2, and by the power rule we're going to do this. Of course, there's plus c, and one thing that you shall not forget is to substitute the original variable back into the answer, because the question was asked in terms of x, not in terms of t, and this is the final answer. So I'm going to type this up: 2 9s 3x squared plus 7 to the power 3 over 2 plus c. And got it. This integral again looks, not again, but some integrals look scary, but we know the hint here is to use the substitution. And usually in the previous problem we took the input for the radical function and substitute it with something. In this case, our only hope is to introduce t as the input of secant, because otherwise we wouldn't know what to do with it. And dt will be 10x to the 4 minus 2 dx. And you see how substitution works now. This whole thing is now equal to integral. Well, 40x to the 4 minus 8, that's pretty much this, times 4. So instead of that, we're going to plug in, well, instead of that and that, we're going to just write 4 dt. And here we just have secant squared of t. So immediately the integral became very simple. It's just 4 integrals of secant squared t dt. And antiderivative of secant squared is tangent. But don't forget, instead of t, put the original function. So you can check your work by differentiating your answer, and you'll see exactly how that chain rule would reappear, and you'll be able to recognize all the ingredients of the chain rule in this integral. Anyway, that's the answer. We're making very small progress, so it could be a long homework. So let's continue. In this case, they suggest which substitution to do, and I don't like them using letter U. I know a lot of people do that, but we are not going to. So t is equal to 9x minus 1. dt is equal to 9dx. And that means what? That means we have an integral of t squared dt, which is 1/3 t cubed plus c, which is 1/3 9x minus 1 cubed plus c. So again, it doesn't matter which letter you use, but I would like you to preserve letter U and V for the integration by parts method that we will learn later in this class. Does this thing even move? 5%. What are we gonna have, like 20 problems here? Or even worse, 40. So here we have integral of negative 10x radical minus 5x squared minus 7 dx. The substitution is t equals negative 5x squared minus 7. dt is equal to negative 10x dx. So we see how this together is my dt. So the new integral will be the integral of square root of t dt, which is 2/3 t to the power 3/2 plus c. And instead of t, we'll write negative 5x squared minus 7. So while the problems are relatively easy keep practicing the overall way of organizing your solution. As when the problems become harder, this will become even more crucial, the ability to organize your work. Here we have an integral, and the substitution, again, we can just follow the rule of thumb and try to substitute the ugliest thing. And usually the ugliest thing is either, well, the times when it works really well is when the ugliest thing is inside of the other function, and the derivative of that thing is also present somewhere in the integral. So in this case, we're doing substitution, replacing t with that, and dt is simply negative 12 x cubed dx. And now we have to be careful, right? So we're going to isolate this x cubed dx and divide dt by negative 12. So the integral now becomes, we still have 5, but instead of this x cubed and dx, we're going to write negative 1 over 12, and I'll put dt right over here. And we're dividing it all by t to the power 8. So simplifying and factoring out the coefficients, we simply have the integral of t to the negative 8 dt. So negative 5 over 12, t to the negative 7 over negative 7 plus c. So on one hand we simplified, so it's 5 over 84. On the other hand, we plug in 5 minus 3x to the 4 for t. And that's the final answer. And as always, the hardest part is to write this without making a mistake. We are making very slow progress here. So hopefully you're not doing it around midnight on Sunday when it's due. Let's continue. So in this case, the hint is we're going to spend more time doing trigonometric integrals in the future, but let me give you the hint. Take t and make your sine of 6x dot t. So actually the other way, sorry. Let's make cosine of 6x ut. So dt will be negative sine of 6x times 6 dx. So if we divide both sides by 2, we'll see, or maybe even negative 2, then we'll see how it's going to become 3 sine 6x dx. So now we see the pattern. We're going to replace this 3 sine 6x dx with this. So we have negative 1/2 dt. And we're dividing it by cosine cube of 6x, which is t cubed. So after all, we have the following integral. And It's just this. And cosine squared is just reciprocal of cosine squared is just secant squared. So let's see if we can impress Newton with our knowledge of trig identities. Of course it knows it. In this case, u is given. And, well, we're not going to be using u, we'll be using t. So, integral of 13x to the power 12 plus x to the power 5, square root of 6x to the 13 plus x to the 6 dx. So if t is equal to that, then dt will be equal to 6 times 13x to the power 12 plus 6x to the power 5 dx, and we can take out 6, or if we divide everything by 6, we're going to have 1/6 dt is equal to 13x to the power 12 plus x to the 5 dx. So we can see how this is now this. So the entire integral becomes 1/6 dt divided by square root of t. So we have 1/6 t to the power 1/2 times 2. I'm very tempted to start skipping problems because they are pretty much repetitive at this point. But let's see. Let me do a couple more. Hopefully it will jump out of this objective. So we're going to go with the suggested substitution. We're going to find dt. This is x. So this becomes this. And we have dt over square root of t, and that's just 2 square root of t plus c, so it's 2 square root of x squared plus 8 plus c. In this one we have So if we take out 3, we're going to end up with exactly what we have in the integrand. And then our integral will become 1/3 dt. And here we have t to the power 8. So the final answer will be 1/3 1/9 t to the power 9 plus c. So 1/27 3x to the 4 plus x cubed to the power 9 plus c. That was 1 of 5. Been sitting here for 6 hours. That's all we accomplished. Okay. In this problem, they don't tell us what to substitute, but this is one of the standard integrals, or it will become one of the standard integrals once we learn it. I mean, we can just go with the rule of thumb here, but also I feel like we can be tricky. So there's also a chance that there are multiple substitutions that could work. So let's try one, and if it doesn't work, we'll try another one. Then dt is equal to 4x cubed dx. And we're gonna do an extra step. We're gonna acknowledge that x to the 4 is equal to t plus 2. So now when we're going to substitute things in, we're gonna split x to the 7 into x to the 4 times x cubed. And we're going to replace x to the 4 with t plus 2. We're going to replace x cubed dx with 1/4 dt. So this is 1/4 dt. And in the denominator we have square root of t. And this one is going to work, of course. So we have 1/4 square root of t plus 2t to the power -1/2 dt, and it makes sense to write this as exponential in exponential form, and then we can easily integrate this, right? So we have 1/4 t to the power 3/2 over 3/2 plus 2 times t to the power 1/2 divided by 1/2, which is another 2, and plus c. So simplifying it, we get 1/6 t, which is x to the 4 minus 2 to the power 3/2 plus x to the 4 minus 2 to the power 1/2, and 4 and 4 gets cancelled. So this is the final answer. It seemed to work. In this case, we're going to do the so how do we know what to substitute? Well, remember, the substitution meant to undo the chain rule. So it really works well when you have the following pattern. You have an integral of a derivative of a function, and then the function, I guess I should be writing g here, derivative of a function times the composition of a function. So this is when it works really well. Just a thought. So when seeing a problem like this, I can immediately recognize that derivative of this is going to be equal to this. So that sets me up with this substitution without too much thinking. And when divided by 1/2, we get negative 5x. And we're pretty much set. We're gonna get integral of 1/2 dt, and here we have t to the power 6, so it's going to be 1/2 17 t to the 7 plus c. So the final answer 1/14 negative 2x to the power 5 plus 4x to the power 4 to the power 7. Well, we're moving along through these objectives, so let's go to the next problem. So we're going to exploit the same pattern, and we're going to notice that the derivative of 3x cubed minus 2x can be related to that expression in the parentheses at the very beginning of the integrand. And we're going to set the variable t to be 3x cubed minus 2x. So dt will be equal to 9x squared minus 2 dx. So if we multiply it by negative 4, we're going to get 8 minus 36x squared dx. That's my ingredients. And plugging everything in, we get what? We get negative 4. And now we have secant t tangent t dt. So that's just derivative of secant. And here's the answer. Now if you try to apply the chain rule to differentiate this function, you'll see exactly how all those expressions will start popping up as you're applying the chain rule. So one problem is 5% of progress, so maybe 9 more problems. Who knows? Let's see. This one looks intimidating, but we just again need to break down What's going on here? I kind of don't even want to write this problem. It's just so much writing. So what are we noticing here? We're noticing that if we were to differentiate this, we're going to end up with this and this. So that tells us that we should substitute exactly that, because we have a derivative of that present in the integral. So dt will be equal to 4 sine cube x times cosine x. And here we have minus 12 sine squared x times cosine x dx. And if we take out 4, so we divide everything by 4, and we factor out cosine x, then you see how this along with this can be just replaced with this. So the original integral now becomes 1/4 of t to the power 6 dt. So we have 1/28 t to the 7 plus c, or 1/28 We are making progress. Still waiting for some definite integrals, and here they come. So when we have a definite integral, we definitely need to be familiar with both approaches. And let me show you the first problem. I'll show you how to do it both ways, but then I'll do it whatever feels more comfortable at the moment. The first approach is to ignore the limits of integration and just treat this problem as we treated like many other problems earlier today in indefinite integrals. So let t be equal sine of x, then dt is cosine x dx. So the problem now becomes 6t cubed times, not times, but dt. And there's a reason why I don't put this limits of integration here, because pi/4 and pi/2 do not apply to t, they apply to x. So I'm just going to write some a and b here, and then I'm going to find this integral. Notice how I'm still not putting any limits. And now that I went back to the original variable, now I can put my original limits back in. And that means we have sine of pi/2 to the power 4 minus sine of pi/4 to the power 4. And the final answer is sine of pi/2 is 1, and sine of pi/4 is √2/2 to the power 4. That becomes 1/2 squared, so it's 1/4. So this is 9/8. So the answer is 9/8. Well, should have read the problem. Because this problem actually is asking me to find this A and B. So we did more than the problem was asking, so we found the answer, 9/8. But let me show you actually how to figure out this A and B and how to finish this problem in an alternative way. So if you at some point decide to actually not do it this way, but change the limits, here's what you do. Instead of just stopping here, you create a table of input-outputs. So this is your old variable, this is your new variable, this is your old limit, this is your old upper limit, and your new limit will be computed using this function. So this will be a sine of pi over 4, this will be a sine of pi over 2. So sine of pi over 4 is root 2 over 2, and sine of pi over 2 is 1. And now that means that we can actually, instead of going back to the original variable, we can pick up here. So instead of a, we'll write root 2 over 2, and instead of b, we'll write 1. And we can continue with the problem here. We put 3/2, and then instead of t to the 4, we'll put 1 to the power 4 minus square root of 2 over 2 to the power 4. Still get the same answer, so it's just a matter whether you understand what to plug in and where to get the new limits. So the new lower bound is square root of 2 over 2, and the new upper bound is 1. So let's do this problem. Integral from -1 to 0, 2x squared over 2x cubed plus 4 to the power 4 dx. And we're going to do this substitution. We're going to substitute 2x cubed plus 4 for t. So dt will be 6x squared dx. That means 1/3 dt will be 2x squared dx. So we're going to be replacing this with this. And we're going to change the limits. So the original variable was -1, 0, and the t variable will be 2 times -1 cubed plus 4, 2 times 0 cubed plus 4. So this limit will be 2, this limit will be 4. So plugging everything in, we get the new integral from 2 to 4. The limits now with respect to t, we replace 2x squared dx with 1/3 dt, and we have what's left is 1 over t to the power 4. So it's 1/3 integral from 2 to 4 t to the -4 dt. So we have 1/3 t to the -3 divided by -3 from 2 to 4, so it's -1/9, 4 to the -3 minus 2 to the -3. Of course, we can simplify it. 1 over 64 minus 1 over 8. Uh, 64 times 9 is 7/572. I presume, but let's see. Hopefully it's the right answer. Let's use Desmos real quick here to check arithmetic. 64 times 9. 576. Well, since I'm already here, let me show you how to check your work in Desmos. Type the integral, the limits, and type the actual integral. And you can type the original integral. And or you can type some intermediate integral, such as we got earlier. So we got an integral from 2 to 4 of 1/3 1 over times 1 over t to the power 4 dt. So also the same answer. This is what happens when you try to do... Oh no. Where did the 5 come from? Did it... No. Well, lesson learned. I'll just skip this problem so I don't waste time actually here. It's a 4% progress. Alright, this problem looks scary, but it shouldn't be scary. We have integral from 0 to square root of pi over 12. And I think the limit can kind of give away the substitution, the way the limit is expressed symbolically. But let's notice that derivative of tangent is secant squared, but derivative of tangent 3x squared by the chain rule will be secant squared 3x squared, and it's going to be multiplied by 6x dx. So if we divide it by 2, we'll get 3x secant squared 3x squared dx. And let's change the limits. This is x, this is t. When x is 0, when x is 0, tangent of 0 is also 0. And when x is square root of pi over 12, we get tangent of pi over 4, which is 1. So the integral is now from 0 to 1 of 1/2 dt, but we have tangent cubed, so it's t cubed dt. So the answer is 1/2 1/4 t to the 4 plus c. So we have 1/8. Oh, sorry, we don't have plus c. Remember, we do indefinite integral. So it's going to be 1/8 1 to the 4 minus 0 to the 4. So the answer is just 1/8. Integral from 0 to 1, 3x cubed square root 4x to the 4 plus 2 dx. Substitution is, this one should be pretty straightforward. So t should be equal to 4x to the 4 plus 2. dt is 16x cube dx. So if we divide it by 16, we'll get that expression. And now finally changing the limit, so when x is 0, t is 2, and when x is 1, t is 6. So we got all that done. So my new integral is from 2 to 6. We got 3, x cubed is 1 over 16 dt, and here we have square root of t. So we got 3/16, t to the power 3/2, 2/3 from 2 to 6. So it's 1/8, 6 to the power 3/2 minus 2 to the power 3/2. And I don't think that can be simplified. So let's try it. 1 over 8, 6 to the power 3 over 2, minus 2 to the power 3 over 2. Here they're only asking for the bounds, so we're not going to do the whole problem. We'll just do the recommended substitution. T is equal to 3x cubed plus 3, and that means when x is negative 3, let's do when x is equal to 0. When x is equal to 0, t is 3, but when x is equal to negative 3, we have negative 81 plus 3, it's like negative 78. So the lower bound is negative 78, the upper bound is 3. And we're on the last objective here. I don't know what the last objective is, but we've seen a similar problem before. We have integral from square root of pi over 12 to square root of pi over 3. The integral looks scary at first, but you just need to crack this substitution code and to realize that sine of 3x squared, derivative of that will be cosine of 3x squared times 6x dx. Dividing it by 6 will give us that. Will give us x cosine 3x squared dx, and we can even divide it by negative here. And then when x is square root of pi over 12, t becomes sine of pi over 4, which is root 2 over 2. And here we have sine of pi, it's just 0. I was just checking the work, and now what do we have? We have integral from square root of 2 over 2 to 0. Negative x cosine 3x squared is just your negative 1/6 dt, and we have t to the power 4. So we have negative 1/6 1/5 t to the power 5 from root 2 over 2 to 0. So it's negative 1 over 30 and we got 0 to the power 5 minus square root of 2 over 2 to the power 5. And this one, so minus minus cancel, so we have square root of 2 to the power 5 over 30 times 2 to the power 5. And square root of 2 to the power 5 is just 4 red 2 and 4 removes 2 from the 5 in the denominator, so it's 2 cubed, so it's 8 times 30, 240. I don't want to make a mistake here, really, but let's just try the first time the answer that we got. And oh, we got it. We got it. Finish line. Another one of this. Again, the only thing you should learn by now is that not to get intimidated by ugly things. And isn't it the same one? Kind of the same one. So maybe pause the video and try to guess the right substitution here on your own. But I'm going to substitute cosine of 3x squared. So then dt becomes negative sine of 3x squared times 6x dx, and then taking negative 1/6 will leave us with exactly what we want. So this will become this, and need to change the limits. Cosine of pi is negative 1. Cosine of pi over 4 is root 2 over 2. So this is my substitution setup. So this integral is from negative 1 to root 2 over 2 of negative 1/6 t to the power 4 dt. So we have negative 1/6 times 1/5 t to the power 5 from negative 1 to root 2 over 2. Looks very familiar. So we have negative 1 over 30 times root 2 over 2 to the power 5 minus negative 1 to the power 5. So let's see if this works. And it worked. And hopefully the last problem. This was the last problem. So hopefully you have seen a variety of problems that are done with substitution. The main goal was to learn the process rather than try to memorize the formula. If you have any questions, feel free to reach out anytime.